Good morning. This is your stats sensei, Mr. Spensei, and we're going to revisit and break down the pinata problem. So, a pinata is a container filled with toys and candy is broken up by hitting with a stick. The drawing above shows Sophia trying to break a pinata. Adorable. The probability that she'll break the pinata on the first hit is 0.2. So, let's talk about that real quickly. So, the probability of break equals zero point 0.2. The probability of does not break equals 1 minus 0.2 or zero point 0.8 on the first hit. She'll continue to hit the pinata until it breaks. If she does not break the pinata on the particular hit, the pinata is weakened and the probability that she'll break it on the next hit is 0.2 greater. So, sounds like our probabilities are changing. For example, if the pinata does not break on the first hit, the probability it'll break on the second hit is 0.4. Now, that's interesting. They say if. That's like saying given that it didn't break. So given it didn't break, the probability it will break on the next hit is 0.4. Calculate the probability she does not break the pinata on the first hit and does break the pinata on the second. Well, so that means we have two events here. We have a first swing and a second swing. Well, the first swing, it cannot break. Well, up above, we just said the probability it doesn't break on the first swing is 0.8. And the probability it does break on the second swing is 0.4. So it has both of these things have to happen. So the probability that not breaking and breaking is the multiplication, which is 0.32. All right? Because really what we're looking for is the probability of not break, intersect, break. That's kind of what we're looking for. Okay, so let the random variable x, notice they define random variable, represent the number of hits required for Sophia to break the pinata. Complete the probability distribution in the table below. Oh, well, the probability it breaks on the first hit is 0.2. And I had some people that wanted to just add 0.2 all the way across, but all of a sudden we get to a probability greater than 1 when we sum them. So that doesn't work. And then it's like, oh, wait a second. We've already figured out the probability that it didn't break on the second one, or that it breaks on the second one, is 0.32. So we're going to start an organization and see if we can't figure out how to work this problem. So probability breaks on the first one is 0.2. So this would be our first attempt, first swing for Sophia. Then we have a second swing. All right, on a second swing, we're looking at not breaking on the first hit and breaking on the second hit. Well, not breaking, we already said up above that the not breaking on the first was 0.8, and the problem told us that this was 0.4. Also up here in the prompt, they said that it would be 0.2 greater. And I noticed that if I go from here to here, I'm adding 0.2. So this is my 0.2 increase. 0.2 plus 0.2 is 0.4. So let's see if this works again. On a third one, we have 3 swings. And we know it's going to break on the third one. That's the plan, but that means it cannot break on the first one and it cannot break on the second one. Well, the probability of not breaking on the first one, we already said was 0.8. And we know the probability of breaking on the third one is going to be 0.4 plus 0.2. So this is 0.6 because all I did was increase by 0.2. But I still have this. Well, this is the probability of breaking. So what's the complement of breaking? That, well, that's not breaking. So 0.4, so 1 minus 0.4 is 0.6. All right. Then we have our fourth. So now we're looking at not breaking. not breaking, not breaking, followed by breaking. Well, we already know that this is 0.8. We already know the probability of this not breaking is 0.6. We know that we have to go, well, this is going to be 0.2 greater. I have to add that 0.2. So this is 0.8. And this is a 0.6 of breaking, but I want not breaking, which is the complement. So the complement of 0.6 would be 1 minus 0.6, which is 0.4. And finally, the fifth swing. So not breaking, not breaking, not breaking, not breaking, followed by breaking. Once again, we already know that this is 0.8. We know this is 0.6. This is 0.4 because all of these are not breaking. We know on the last one, we have to be 0.2 greater, so adding 0.2, so this makes this 1 whole. All right. And finally, I need the complement of breaking because this is breaking and I need not breaking. So 1 minus 0.8 is 0.2. All right, 0.8 times 0.4, that equals the 0.32. If I multiply 0.8 times 0.6 times 0.6, I end up getting 0.288. And then the next one, 0.8 times 0.6 times 0.4 times 0.8, that equals 0.1536. And then ultimately, multiplying all these together, I end up getting 0.0384. Well, here's the question. Did I do this right? Well, there's actually a little bit of a check. And the check would be this. Add up my probabilities and see if they sum to 1. So 0.2 plus 0.32 plus 0.288 plus 0.1536 plus 0.0384. When I do that, it sums to 1. So this makes this a valid probability distribution. So I probably took care of that and did that part right, correctly. All right. It says calculate and interpret expected value of X. And really, this was calculate, and this part was supposed to be interpret. So it wasn't supposed to be occur twice. Well, first off, a quick way to do that is to go to stat edit. And I do have something to say real quickly about all this. And that goes like this. If you had struggled with this, which is completely acceptable, if you had struggled with this and you go, well, I don't know the answer, so you put in some probabilities in here, and I would try to make sure that they sum up to 1. But if they did sum up to 1, and you put the probabilities in there, and then you worked out this bottom part, you could still get credit on the bottom part, even though this was completely wrong. All right. So don't make sure that you, at the very least, put some reasonable probabilities in there, which in my case would say that they sum up to 1, even if they were completely wrong. And actually get the extra credit, or not extra credit, but get that credit for those problems. So stat calc 1-bar stat L1 L2, and I find out I expect it to break in about 2.5104 hits, but I have to show my work. Well, our work is simply this times this plus this times this plus this times this plus this times this plus this times this. Well, they've already defined my variable. So the expected value of X equals 1 times 0.2, and that just came from here. Then 2 times 0.32 plus dot plus 5 times 0.0384. And that happened to equal, and we said that that equaled 2.5104. And the interpretation is, in the long run, we would expect it to take an average of 2.5104 swings to break this type of pinata when Sophia is swinging. All right, so basically, it's not just any person swinging, because I mean, Derek Jeter probably break it in the first hit, but Sophia is probably going to take her an average of 2.5 swings to break this type of pinata. Other pinatas may take longer, some may be faster to break. But that's our answer. I hope this was helpful. And once again, these probabilities had to sum to one whole, and it's increasing as we go this way. Then we have to use the complements for the rest of it. And I've got to tell you that for your test, it's super, super important to understand the concept of complements. All right. Appreciate you watching, and I will see you on the next one. This is your Stats Sensei.